He finished his PhD in 2019 in Granada, working in the nonlinear regime of QCD in the context of heavy ion collisions. And since then, he has done several postdocs, including École Polytechnique, UASCLA, and now more recently, he joined the Pheno group here at LIP last year. So Pablo has several works on color glass condensate, elliptic flow, some of which are, okay, you will hear today, some of which are about initial state physics that are having an impact of the field. So this is exactly the topic of today's seminar. So Pablo, you can start whenever you want. Thank you.
Okay, thank you for the introduction, Liliana, and also thank you and Valentina for the invitation to give this seminar. So my understanding is that the LEAP community is quite diverse and also mostly experimental. So in this introduction, I try to describe the main theoretical aspects of the work and also try to make a clear relation with phenomenology and experiment. So first of all, let me take a quick look to the standard picture of heavy ion collisions. Right at the start, we generate a highly dense out of equilibrium state called Glasma. Then the Glasma evolves through multiple scattering and quickly thermalizes into a Quark Gluon Plasma. The Quark Gluon Plasma, or QGP, is deconfined matter. It's formed of deconfined quarks and gluons. So it will eventually rearrange into hadrons. And these hadrons will eventually fly through the detectors along with some other kinds of radiation. So by analyzing the non-trivial correlations between these sometimes thousands of particles, we are able to learn about the different properties of these phases of the evolution. But in particular, we are going to be interested in learning about the properties of QGP. Of course, each of the phases of this evolution are interesting in their own right, but I think it's fair to say that the main goal of the heavy ion community is to reduce the uncertainty in describing the QGP. In doing so, we encounter several difficulties, and one of them is that some of the experimental signals that we look for here are deeply affected by the initial stage of the collision. The problem with this is that we still don't have a completely robust and definitive theoretical description of the initial stage dynamics. And instead, one has to rely on phenomenological models that, as I will explain later, make it a bit difficult to discriminate between initial state and final state effects. A good example of this is given by the study of collective flow. This is a phenomenon that indicates that at some point in our collision, we might be generating a fluid state, which in the QGP we identify, which in the heavy ion physics context we identify with the QGP. So the experimental observable associated to this phenomenon is called Azimuthal anisotropy and is characterized by the Fourier coefficients of the particle spectra. These are harmonic flow coefficients, and as you can see here, they can be extracted from data as a function of the centrality of the collision. So these measurements can be analyzed in a fluid paradigm that can be roughly summed up with this cartoon. First of all, we would have an initial stage that features a certain spatial deformation. And then the expansion of the medium would map this deformation that we cannot see into a momentum anisotropy that we can actually measure. So in order to translate this picture into phenomenology, we would need, first of all, a certain model that gives us the initial conditions. And these initial conditions are fed into a hydrodynamical simulation of the Quark Gluon Plasma expansion. Then the outcome of this simulation is compared to experimental data. And through this comparison, we are able to constrain the values of the physical parameters that enter in both the initial state model and the medium simulation. So this strategy is effective and it has been used for more than a decade now, but it has some shortcomings. And in order to see that, let me focus in this first step, the modelization of the initial stage. So the traditional way of doing this is based on what we call the Glauber Monte Carlo ansatz. Basically, what we do is performing a random sampling of the position of nucleons in the colliding nuclei according to a Booth-Saxon distribution, for example. And then we assume some mechanism for energy deposition in order to map this into an energy density profile. Then from the energy density profile, we are able to compute eccentricities, which characterize the spatial deformation of one event. But of course, in collider experiments, we are not really interested in individual collision events, because what we actually have access to is some quantities that depend on the average and the fluctuations around this average. So in this talk, I will focus mostly on the fluctuations. So there's a number of reasons why this initial stage can fluctuate from one event to the other. And the most obvious one is the first step of this process, which is the random sampling of nucleon positions. This is known as geometrical fluctuations, and it's normally the dominant source of fluctuations. But in addition, we could also consider the subnucleonic structure. For example, a hotspots model. Here we will assume that the gluons tend to group around the valence quarks, and the position of these gluonic hotspots would provide an additional contribution to the fluctuations. And finally, we could also consider the quantum fluctuations of the wave functions, which modify the density of color charge densities on an event-by-event basis. So all that I've talked about here in this slide is basically a phenomenological ansatz, and in principle, we don't know how important each of these contributions are with respect to each other. In fact, this is something that changes from one prescription to the other, and there is really nothing preventing us from doing some fine-tuning in order to find the best available description for the data. The downside of this is that we don't really get to learn about the underlying physics of the fluctuations. And for that, we would need some theoretical input. So with this motivation, we resolved to perform a series of studies focused on the quantum fluctuations in the wave functions, because this is a source of fluctuations that we expect to be able to describe from first principles in QCD. So let's see what QCD tells us about this. So we have that in the high energy limit, the wave functions of the colliding hadrons are dominated by large densities of soft gluons. This is not only a prediction of the theory, but also it has been measured a long time ago, as you can see in this old plot of the proton PDFs measured at HERA. These gluons are generated through radiative processes where the probability of emitting a new gluon depends on the gluons that have been emitted so far. So this mechanism leads to an exponential growth of gluons that, of course, cannot go on indefinitely, because that would lead to a violation of unitarity. We reach a point where the area density of gluons becomes so large that we have to start taking into account gluon recombination processes. So when these non-linear effects become as relevant as the linear radiation processes, we say that the wave function of hadrons have become saturated. They have entered the saturation regime. So this is an effect that would happen universally in all the hadrons, but with this I just want to remark that is an effect enhanced in nuclei due to the larger ab initio density of gluons. So the hadrons that have entered the saturation regime can be described within an effective theory called Color Glass Condensate, or CGC. This theory is based on a classical approximation where we are basically taking the large density of gluons carried by the hadrons and replacing them with a strong color field. By doing this, we are basically taking advantage of the fact that A large occupation number is approximately equivalent to the presence of a classical field, because the quantum fluctuations represent a negligible correction to the strong background field. So the dynamics of this field are described by the Yang-Mills classical equations. And at this point, you can see that I am performing an explicit separation of degrees of freedom. On the one hand, we have the low momentum degrees of freedom, which are the gluons, represented by the classical fields. And on the other hand, we have the valence quarks, which are the sources of the classical fields, and which enter the Yang-Mills equations as a color current proportional to the color source density, this rho that we have here. So in order to describe the event-by-event fluctuations that we are interested in, we are going to treat these rhos as stochastic variables. And then we are going to compute our observables by performing an average over all the possible configurations of these densities. So as you can see here, we have assumed that the statistical weight associated to this process is a Gaussian. And okay, this might seem a little bit too simplistic, but it's a good approximation when we are talking about big nuclei, when we are talking about large mass numbers. This is because we are talking about relativistic collisions. So these ions are going to appear to be very Lorentz contracted. And therefore, the color source densities that we have here are the result of the overlap of the distributions of many nucleons. So if we assume these distributions to be independent of each other, we can invoke the central limit theorem. And basically, we have that this distribution would tend to a Gaussian. Anyway, this choice is the main characteristic of the McLerran-Venugopala model. And the main result of this model that we are going to apply extensively in these calculations is the basic two-point correlator. As you can see, in this correlator, we are assuming local correlations in transverse, longitudinal, and color space. So it's basically as simple as it gets. And this is what is going to allow us to obtain analytical results. This mu squared is a parameter of the model, and is proportional to the number density of color sources. And eventually it will also be proportional to our definition of the saturation scales characterizing each nucleus. So this is not everything that there's to it. This is not everything about the color glass condensate. We also have a renormalization group equations that describe the evolution of the hadrons in energy. But here I just wanted to present the theoretical tools that we are going to be applying in the following calculations. So with that out of the way, let me move on to the next part of the talk, where I will apply this framework to describe the initial stage of heavy ion collisions. So the first thing that we need to do is computing the gluon fields carried by the nuclei before the collision. So in order to do this, we have to solve the Yang-Mills equations with one source. And if we do this in the light cone gauge, we obtain these purely transversal fields that we call alpha 1 and alpha 2. As you can see, they are built in terms of the Wilson lines, which represent the effect of the interaction between valence quarks and the background gluon fields. In the iconal approximation that we are implicitly applying, this interaction gives rise only to a color rotation, which is built here as a path-ordered exponential of the color source densities. So this is a necessary step that we have to take before going to the actually interesting thing, which is the medium generated in the collision of two nuclei. To obtain this, we have to solve again the Yang-Mills equations, but this time we have to do it with two sources. And unfortunately, these equations don't have an analytical solution, except for a very specific region of space-time, which is an infinitesimal proper time after the collision. Here we call this the tau equals 0+. So in this specific region, we are able to obtain the electric and magnetic fields of the Glasma in terms of this nonlinear combination of alpha 1 and alpha 2. Once we have this, we can compute the energy density, which I call epsilon 0 at tau equals 0 plus. And once we have this, we can start thinking about how it fluctuates on an event-by-event basis. And to characterize this, we will compute the 1 and 2 point correlators in the CGC. So in order of difficulty, let's start with the 1 point correlator, which corresponds to the average energy density. So when we expand everything in terms of alpha 1 and alpha 2, we arrive at this expression, where, as you can see, we are assuming that the correlators factorize for different nuclei. So this object depends on the 2-point function of gluon fields, and this object is called the Weizsäcker-Williams gluon distribution. As you can see, this correlator can be decomposed into an unpolarized gluon distribution and a linearly polarized distribution, which are related to the corresponding momentum space UGD by these Hankel transforms. In Gaussian models, such as the one that we are applying, these objects are not independent, but they can in fact be computed from the gluon dipole amplitude. This object plays a very important role in the color glass condensate, and in fact, we have different parametrizations available. In these works, we are going to focus in these two, the GVW model, and a modified version of the MV model, where we have introduced a gluon mass as an infrared regulator. So these models give rise to these gluon distributions, and really all that I wanted to remark from these expressions is that in the ultraviolet limit, the corresponding MV distribution has this 1 over chi squared behavior. So this behavior is in qualitative agreement with D-glap evolution, and this is not something that we can say about the exponential fall of GVW. So all that I'm trying to say with this is that the MV model is more physically realistic. But on the other hand, the GVW is more simple. It's in fact the most simple model that can reproduce saturation. So this is why we will compare these two in our final results. In any case, when we substitute these expressions, we arrive at this general result where the average energy density is proportional to this product of gluon distributions in the ultraviolet limit. In the GVW model, this is not a problem because this yields a very simple expression in terms of the saturation scales of each nucleus. But in the MV model, we have that this object is logarithmically divergent. So this divergence is due to this perturbative tail of the MV distribution, which is one of the main features. But if we want to obtain finite results, we have to regularize it in some way. At this point, we could use a momentum cutoff, or if we were working in the lattice, we could use the lattice spacing as a cutoff. But here what we did was using this running coupling prescription. So we will assume that the coupling constants of these overall coefficients run with the correlation distance R following this formula. And by doing this, we obtain these finite results in the ultraviolet limit. Furthermore, if we do this, if we make this definition for the saturation scale, we have that the gluon distribution tends to the GVW result in the ultraviolet limit. So the takeaway message from all this is that with this prescription, we obtain finite results while simultaneously preserving this power law tail that characterizes the MV model. So now let me quickly discuss the 2-point function, which corresponds to the variance of the energy density. As you can see in this case, the result depends on the 4-point function of gluon fields. And the calculation of this object, even in the Gaussian approximation that we are using, is quite challenging. So what is usually done is basically assuming that we can write everything in terms of 2-point functions. This is called the Glasma Graph approximation. This is how it's known in the literature. And it has been shown to be appropriate for short distances, as we will see later. By applying this approximation, life is so much easier, and one obtains this very compact expression and these curves, where we compare GVW and MV models. As you can see, the MV model shows a faster decay, but in the end, these results are not so different from each other. However, we have to remember that this is obtained for only an infinitesimal proper time after the collision. So let's step back and see the bigger picture. Here, the results that I've talked about so far, were obtained previously in this paper by Thomas Lappi and Soren Schlichting, with some differences in the running coupling prescription. But then later in this couple of papers, me and my collaborators computed the same correlations, but going beyond the Glasma Graph approximation. So this is kind of a very technical part of the talk, but let me quickly outline how this calculation is. So first of all, in order to perform this calculation, we need to write the gluon fields in terms of the color source density and the Wilson line, the adjoint Wilson line, just like this. By doing this substitution, our four-point function can be expanded into this expression. And as I mentioned before, this formula is the source of many technical challenges. The first of them is that this correlator cannot be factorized into separate correlators of Ross and Wilson lines. This is something that can only be done with the two-point function of gluon fields. But in this situation, we have mixed correlators, and these are highly non-trivial to compute. And the whole process gives rise to a total of 7 terms, as you can see. So this might not seem like much, but note that the product of these two correlators gives rise to 49 terms right off the gate. So some of these are quite difficult to compute. And for example, some of these terms include projections of the correlator of 4 Wilson lines. And this operation implies performing projections into color neutral states. So in the case of 2 Wilson lines, this is relatively simple, but doing it in this case requires the use of quite advanced color algebra techniques. So once we solve this problem, we find yet another technical challenge, which is the fact that the contraction of all these indices with the prefactors of the correlators is quite non-trivial. And in fact, in order to do that, we have to resort to computational tools. Specifically, we have to use the fine calc tool of Mathematica. So overall, this is a huge calculation, and it gives rise to this formula, which seems quite big, but it's surprisingly compact, taking into account the process to get to it. So now that we have this, let's compare it to the Glasma Graph result. And as you can see, the Glasma Graph is a good approximation at short distances, but it breaks down around 1/QS. I am sorry if you cannot see this very clearly, but I forgot to put this in a log scale. But it breaks down around 1/QS. And then after that, the curves feature different power law tails. So this discrepancy doesn't have a big impact on the qualitative conclusions about the energy density fluctuations, because the energy density is a quantity largely dominated by ultraviolet modes. But it is quite relevant when we are talking about quantities that are sensitive to the infrared. And this will come into play later. But for now, let me go back to this slide. As I said, these calculations are performed for tau equals 0+. But in the end, if our goal is to study the initial conditions for the Quark Gluon Plasma, then we should be able to say something about this gap. And this was the topic of the paper that I will talk about now, which was published in collaboration with Thomas Lappi. Here, we asked ourselves, how does the energy density distribution evolves through the pre-equilibrium phase? So as long as we stay in the classical regime, and this is our main assumption here, this evolution should be encoded in the Yang-Mills equations with 2 sources. Here I am writing this equation in terms of the color source densities of each nucleus. And now, because this is a relativistic collision, both of these nuclei appear very Lorentz contracted, as I said before. So in order to reflect this, we will take the color sources as delta functions in the respective longitudinal directions. Because of this, when we consider finite values of tau, the Yang-Mills equations become homogeneous. Here I am writing the separate components of the equations in the coordinate system defined by tau, pseudo rapidity, and the transverse plane. So this is the system that we have to solve. And as I mentioned before, it has no analytical solution for finite proper times. The standard approach is to apply numerical techniques, taking the solution at tau equals 0 plus as boundary conditions. But in this project that I want to talk about now, we try to look for an analytical approach to this problem. And our strategy was basically linearizing the Yang-Mills equations. By doing this, we are explicitly neglecting all higher orders in the gauge potentials. So the safe thing to do, the convenient thing to do would be look for an appropriate gauge where the amplitudes of the neglected terms are minimized. A natural choice is given by the Coulomb gauge, which minimizes the amplitudes of the transverse components of the fields. And by adopting this and assuming a free dispersion relation, we arrive at this solution. Now we would have to find the initial conditions, and we do this by matching these expressions to our tau equals 0 plus results. By doing this, we obtain these two expressions, and in turn, from these gauge fields, we can compute the electric and magnetic fields of the Glasma, just like we did before. As you can see, the results are expressed in terms of the initial conditions times Bessel functions of the first kind, which contain the proper time dependence. And at this point, I should mention that I am cheating a little bit because we perform this matching without explicitly finding the gauge transformation to Coulomb gauge. Basically, we are taking advantage of the fact that the specific quantities that we want to study are written in terms of the electric and magnetic fields of the Glasma, but they don't depend explicitly on the gauge fields themselves, which is why we will use these components in the following calculation. So because we want to work in coordinate space, we will also do this. We will Fourier transform the initial conditions and then identify this integral as the initial condition in momentum space. Then from this, we can write down the tau dependence in coordinate space. And by performing similar steps, we can do that with every component of the Glasma. And this is really all that we need to start talking about correlators. Again, we start with the easiest one, the one-point correlator. And as you can see, the evolution is obtained as a convolution of the initial conditions with this combination of Bessel functions. These Fourier transforms can be computed explicitly, and we arrive to this expression. And here we can see that the average energy density results from the interference of the Weizsäcker-Williams distributions of each nucleus, with this factor controlling whether the interference is constructive or destructive. Now, if we substitute the GBW model results, and we keep performing these integrals, we eventually arrive at this expression where the remaining integral here is performed numerically. As you can see, the effect of tau evolution can be described as the initial average energy density times a non-trivial dilution factor, which describes the decrease of energy density with time. As you can see, this decrease is remarkably more pronounced in the case of the MV model, especially at early proper times. And now let's take a look at the two-point function. And you can see that just in the previous case, we have the initial conditions convoluted with these Bessel functions. And we can repeat the same steps as before. And this time we will only apply the Glasma Graph approximation. In the previous calculation, we were able to go full MV, but because we only had to deal with two different transverse components. But in this case, we have 4. So that makes it much more complicated. And yeah, this is some work to do in future projects. But anyway, in the Glasma Graph approximation, we get to this simple result. At this point, let me remark that these integrals are performed numerically for every value of tau and the correlation distance. And we do this for 3 different values of the proper time, obtaining these curves here. On a quick look, one could describe the general trend of this evolution as an increase of the correlation length. This is one of the effects that we expect to happen in any system that is approaching the hydrodynamical regime. So this result is in agreement with our intuition of how the evolution would go. But it's not the whole story, because we don't expect this calculation to be valid throughout the whole pre-equilibrium period. In fact, these calculations are based on a classical approximation that is expected to break down at some point because the Glasma keeps evolving and becoming more and more dilute. So there comes a point where the classical approximation no longer holds, and it has been argued that at this point, some effective kinetic theory should provide the intermediate step between the classical region and the hydrodynamical expansion of the QGP. This is out of the scope of this talk, so I'll just list these references here, because for now we are going to focus in the classical regime. But if we are going to do this, then the logical question would be, what can we use these results for? And I will try to answer that question in this next part, where I will discuss how we applied some of these results in the study of azimuthal anisotropy. So let me start by briefly going back to this slide. Here I am showing you again the typical approach to describing the initial state of a heavy ion collision. And here is what we have done so far. Instead of considering the collision of 2 nuclei with multiple nucleons distributed randomly, as in here, we simply consider the collision of 2 slices of color glass condensate. Then we use the McLerran-Venugopala model in order to characterize the resulting fluctuations of the energy density. And we do this by computing these 2 objects, the 1 and 2 point functions. Then from here, the next step would be to characterize the deformation of the medium, which is done by computing the eccentricities. So to do this, we followed the formalism proposed in this paper here, where they consider the energy density to be equals to the average value plus some small fluctuation. Under this condition, we are able to perform a perturbative expansion in order of these small fluctuations. And from this expansion, we can obtain analytical expressions for the cumulants of the eccentricities in terms of the 1 and 2 point functions that we obtained before. So at this point, I have to mention that both eccentricities and harmonic flow coefficients are defined for individual collision events, and therefore they are not experimentally accessible. What is actually measured in experiments is averages of these quantities over specific centrality classes, and these correlations are inferred from 2 and 4 particle, from 2 and 4 particle correlations, and this is what we call the cumulants of eccentricities. And this, as I said before, these are the objects that are going to be actually interesting for us, and these objects depend on the averages and 2 point functions of the energy density. So a crucial aspect about these expressions is that they feature an integration over the transverse plane. So in order to do this integral, we have to introduce the geometry of the collision in our calculation, which we do by making the saturation scales proportional to the nuclear area density of the corresponding nucleus. Then a crucial aspect about this integral is that it is dominated by the long distance behavior of this 2 point function. And as I mentioned before, this is an issue if you are using the Glasma Graph approximation. To see this, let me go back to these results at tau equals 0 plus. As I said before, this discrepancy at long distances is quite relevant when we are talking about quantities that are sensitive to the infrared. And this is the case of the eccentricities. And this is why for this calculation, we will use the full MV results, the big complicated formulas that I showed you before. By doing this, we obtain these results. And here I am showing you the cumulants of order 2 and 3, which respectively quantify the elliptic and triangular deformation of the medium. Also, for comparison, I am showing you the results given by the Trento model, which is a Monte Carlo model based on the Glauber picture. As you can see, our results agree very well in the case of the elliptic deformation. And this is not a surprise because this object is largely determined by the geometry of the collision. And the main difference between these two approaches that I'm showing here is the treatment of the fluctuations. So in order to see the difference, we should have to look for a quantity that is more sensitive to fluctuations, such as the triangular deformation. And here you can see that our result yields a slower growth than in the Monte Carlo model. And this makes sense because we are only considering one source of fluctuation, which is the primordial QCD fluctuations. So now that we have the initial eccentricities, we have to somehow account for the expansion of the QGP in order to compare to experimental data on harmonic flow coefficients. So a truly thorough approach would require us to perform the whole hydrodynamical simulation, but fortunately there is a way around that because of this approximate linear relation between eccentricities and harmonic flow coefficients. This empirical formula is satisfied for central collisions, not only by these quantities, but also by the aforementioned cumulants. So we will apply this simple relation to match our theoretical calculations with data. And we will use these kappas, these response coefficients, as free parameters. So we do this with data taken from the LHC and RHIC. And you can see that we obtain a pretty good description for centralities up to 20% in the case of LHC and for the whole centrality range in the case of RHIC. We do this with reasonable values for our free parameters, which are these kappas and the QS0. QS0 is, it can be interpreted as the saturation scale in the center of the colliding nuclei. So as I was saying, the values of kappa 2 and kappa 3 are comparable to the ones obtained in state-of-the-art hydrodynamical simulations. And the value of QS0 is slightly smaller, which makes sense because we are only considering one source of fluctuation. So we need to make this contribution larger in order to compensate. So to do that, we have to decrease QS0. But beyond these details, the main message here is that we are able to obtain a good description of data based on first principle QCD calculations, even without resorting to other sources of fluctuations. In turn, this paves the way for a series of future research projects and future applications to phenomenology, which is what I would like to discuss in this last leg of the talk. Okay, so to sum up, what we just did was mapping results in coordinate space to measurements in momentum space, and we do it with this simple formula. But a logical next step would be to repeat this kind of a study by using the tau evolved correlations that we have already computed. So this would be a very interesting continuation of our work, especially taking into account that the trend that we observe with Glasma evolution can be described as a correlation length increase. This means that these correlations might become more important at large distances, and this suggests that the contribution of these fluctuations might be even more important than what we had concluded in these previous studies. However, this is speculation, and we won't be sure until we have reliable results. And to do that, we need to compute the time evolution beyond the Glasma Graph approximation, which, as I mentioned, is proving to be extremely challenging. Another potential research direction would be including an additional source of fluctuations by considering asymmetrical collisions. Within this setup, we would have normal QCD, CGC fluctuations in the dense nucleus. And then on the dilute side, we would have, in addition, the fluctuations of the position of hotspots. On a technical level, this would mean that depending on the nucleus that we are dealing with, the correlators that we compute would be computed differently. On the one hand, the averages over color sources corresponding to the dense nucleus would be the typical McLerran-Venugopalin correlators. And in the case of the densities from the dilute nucleus, the correlators would be promoted to double correlators. Here we would not only be averaging over color charge configurations, but also the positions of hotspots. As you can see, we would assume probability distribution for these positions also by using a Gaussian approximation. And as you can see, this factor here would correspond to the QCD fluctuations inside the hotspots. So this setup was already applied at tau equals 0 plus. And in a study that is quite similar to what I was talking about so far. They perform a calculation of correlators, and then they apply it into eccentricity computations, only that in this case they are only talking about proton nucleus collisions. So again, the next logical step would be to repeat this work, but using correlators evolved in proper time. So this calculation could provide an extra constraint of the parameters of the hotspot model, such as the proton radius, the size and numbers of a number of hotspots, etc. And finally, I would also like to mention that this kind of calculations can also be applied to the study of the chiral magnetic effect, which I will briefly explain here. As you might know, the off-central heavy ion collisions, such as this one, give rise to large background electromagnetic fields. And when these fields are in the presence of deconfined axial charge, they induce a separation of charges that in turn generates an electric dipole along the direction of angular momentum. So this phenomenon should define a preferential direction for the emission of charged particles, and this would translate, experimentally speaking, into non-trivial azimuthal correlations in the hadron spectrum. However, it is extremely difficult to relate these signals to the chiral magnetic effect because there are a lot of experimental backgrounds and theoretical uncertainties. So this is a topic that has gathered a lot of attention recently, even giving rise to a dedicated isobar collision program at RHIC. So we argue that in a similar way to what we did with the energy density and the application that we did to Azimuthal anisotropy, we should be able to characterize one of the contributions to the initial distribution of axial charge using the color glass condensate. And then we should be able to relate these results to the specific correlators associated to the chiral magnetic effect. So in this case, the theoretical part of the project is already done because the calculations are completely analogous to the ones that I showed you before. However, the application to phenomenology seems to be a bit more tricky, or at least it might require something more sophisticated than just a simple linear formula. The bottom line is that we consider this to be a quite interesting research direction, and we hope it will give rise to new results soon enough. And okay, here are my conclusions, and yeah, I'll just leave it here. Okay, thank you.
Thank you, Pablo, for this very nice seminar.